Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. In this video, we're going to be talking about the differences between K sub C and K sub P. In our last video, we learned how to write the equilibrium expression for K sub C, which uses brackets because the brackets represent molarity, and molarity represents concentration. Well, what do you think K sub P is? Well, K sub P is going to represent the pressures instead of concentration. So instead of brackets, okay, we're going to use capital P to represent pressure. So it's still going to be the products over the reactions, but it's going to be the pressure of just the NH3 to the second power. And we call this partial pressure when we do P sub NH3. What that means is the partial pressure of NH3, okay? No brackets, okay? And then this is going to be the partial pressure of N2 to the first power times the partial pressure of the H2 to the third power. Now, I'm not going to get the value of 0.105 because molarity is not the same thing as pressure, okay? For example, one molar is not equivalent to 1 atm in pressure, okay? Now, I should still end up getting a small number, okay? Because remember, this small number is favoring the reactant. So when I get this value, when I calculate the value, I should still get a small number because it should still favor the reactants because the K sub C favors the reactants, okay? And then the big question becomes, well, how can I take this K sub C value that we got in our last video and calculate the K sub P value? Because there is actually a way that you could do this, okay? And the way you do that is by using our favorite equation of PV equals nRT. So we're going to take PV equals nRT, and we're going to solve for pressure. So pressure is going to be equal to nRT over V, okay? And this portion right here, moles over volume, that's actually what molarity is. So pressure is actually equal to the molarity times this RT. So the difference between pressure and molarity is going to be a factor of RT, okay? So what I'm going to do is I'm going to substitute in MRT for this pressure, and for this pressure. So let's see kind of like what that K sub P value would look like. Well, in the numerator, instead of pressure, I'm going to do molarity of the NH3. And remember, that's going to be multiplied by the factor of RT, and all of this is going to be to the second power. So the substitution of P for MRT is something that looks like this, of course, to the second power. And I'm going to do the same thing for the nitrogen and the hydrogen. Okay, so the nitrogen is going to look something like this, N2 to the RT, and that's going to be to the first power, okay? And then the hydrogen is going to be H2 RT, and that's going to be to the third power. So we're going to get something that looks like this. Okay, now in the next step, what I'm going to do is I'm going to separate the molarity from the RT. Okay, and it's going to look something like this. Okay, now when I do that, I want to remind you that this too, it counts for the temperature, it counts for the R, and it counts for the molarity. So it's going to end up looking something like this. I got to have my NH3 to the second power times the RT collectively to the second power. Okay, I'm going to do that for the N2. Now that's to the first power, so it's going to be RT to the first power. And then I'm going to do that for H2. And that's going to be to the third power. So its RT is going to be to the third power. So what K sub P is now equal to is going to be this guy right here. Okay, well, what is this guy equal to? Well, that is equal to K sub C. So Kp is equal to Kc times a factor of RT. Now, in this case, if we have RT to the second power as the numerator, and RT to the first power and to the third power, okay, if you know anything about exponents, when you divide, you're actually subtracting. So 2 minus 1 minus 3 would be to the negative 2 for this particular problem, okay? Now, I want to remind you of where these exponents came from, okay? Remember, these exponents come from the balanced chemical equation, okay? So really what this exponent is going to be the change in moles throughout the experiment, okay? So in this case, we have, if we're doing change in moles, remember it's always final minus initial, so we got 2 moles on the final side and a total of 4 moles on the reactant side. So 2 minus 4 moles would be a negative 2 for the exponent, and that's what we get here. 2 minus 1 minus 3, okay, that would be a negative 2. So let's just kind of plug in all the numbers, okay? K sub P is equal to Kc, which is equal to 0.105, times RT. Now, the R value that you're going to use is the ideal gas constant, and it's the 0.08206 version, okay? And this temperature has to be in Kelvin. So to get this into Kelvin, we're going to have to add 273 to get it into Kelvin, and that's going to come out to 745 K. So I'm going to take that times 745, okay, and the change in moles is going to be negative 2. So in your calculators, go ahead and take 0.08206 times 745 and take that to the negative 2 power, okay, and then multiply it by 0.105, and you're going to find out that your K sub P value comes out to be 2.81 times 10 to the negative 5th. And my question to you, is that a small number? Heck yeah, it is. Anything times 10 to the negative 5 would be a pretty small number because we would move this decimal place over 5 times to the left. Now, a small value of K sub P being equal to 2.81 times 10 to the negative 5 means that it's going to favor the reactants being a small number. Just the same way the Kc value is a small number, it's smaller than 1, and it's going to be favoring the reactant side. So in this video, I hope you learned 2 things. Number 1, how to write the equilibrium expression for K sub P and how it's different than K sub C. And then the second thing that I hope you figure out is how to convert a K sub C value into a K sub P value so that you can compare the two. And if you found this content helpful, please give it a like and subscribe. When you add a comment, it really pushes this information out to other students that are interested in learning chemistry.